Let's move away from AI down a level below. AI, of course, is all basically machine learning in the background, and we provide a lot of tools for allowing people to do their own machine learning type tasks, build their own models. And one common paradigm, which actually comes up a lot with providing knowledge to LLMs as well, is vector databases. If we look at semantic search, which is built on top of vector databases, we have basically a very simple mechanism for building indexes that are semantic. So here I've got a database of facts about animals, and I'm just going to quickly build a semantic index, search index for those facts. And so you can see single command here. We've built an index. I can deploy this in the cloud if I wanted to share the index with you. But this basically represents a vector database of the semantic meaning vectors of the words. And it goes nicely with this command semantic search that says for a given index, I'm interested in canines. Give me just one response from the database. So even though the word canines doesn't appear in my database, the semantic nature of it knows that dogs are the nearest word to canines. And so this is the search result that it's come back with. And this is a scalable thing for very large quantities of these vectors. So the underlying mechanism, as I said, is a database for vectors. So you can also roll up your sleeves and use that in any way you want. So here's me doing the same kind of thing, but for images, but taking control of all of the steps. So I've got some images, and I'm going to go to the Wolfram neural net repository and fetch a model that is trained on image recognition, but I've done a net drop to say I only want the last layer that has actually some vectors in it, and put those vectors into a database. So it's the same kind of thing, but I've got here now 6 vectors that represent the features of those images. And then I can repeat the process by saying, find the matches that have similar semantic vectors to this image, and we find the images it considers the closest match. So I had squirrels and monkeys in the data set. I gave it a picture of a monkey, and it found me monkeys. Right, on to some other things. We've had things like classify and predict, and net train for doing machine learning models yourself. We've had for quite a while support for GPUs, but only support for CUDA up to now. And in this release, we're adding Core ML and Direct ML support. So CUDA is the proprietary language for interacting with NVIDIA GPUs. They are the biggest company in the world for doing GPUs, but they're not the only ones. And in particular, this particular timing here, I ran on my own personal Mac. We've not had Mac support for GPU before, but I think it's Core ML is the Mac technology that we can use. So now we're getting GPU acceleration on the Mac. And this is just using one of our repository models, net model. Takes what is that, a 30th of a second to identify that as a tiger, but it's about 10 times faster if I add target device goes to GPU and run that using the GPU hardware, not the CPU hardware. And so there's been improvements to things like net chain and net graph to try and make that something that can generally be benefited from in both training and execution. We've had regression for an awful long time, since probably the first version of Mathematica, where I can take data such as these 4 numbers and say, let's fit a linear model to that. And x minus 2 is our best fit model. We're always trying to make the system join up better. So for a while, we've had uncertainty, error bounds that are a representation of a number with a uncertainty interval on it. And now we've added that support for that. In the last few versions, so since about version 12, we've been making sure all of the functions like mod and sine all do sensible things with intervals and uncertainty. We're now adding that to higher level functions. So now when I do the same data, the numbers are all the same, 0.8, 0.2, but the errors are different. So I've added more uncertainty on this final number. Maybe the experiment that I got it from was a less reliable piece of equipment or something. And fit to that same numbers, but different uncertainty, it now takes into account the uncertainty in the values to give me a different fit. And if we look at that visually, you can see what's going on here. The blue line is the old fit that we had, which does its best to get as close as it can to all 4 numbers. But once we tell it that there's a lot of uncertainty in the 4th number, then the orange line is allowed to be a bit more relaxed about being near that 4th number. It wants to make sure it maintains it's within the error bounds if it can. And it's clearly within the uncertainty interval of that number. But now it's on average closer to the other numbers by allowing it to be more relaxed about this one. And we also have the same if you have uncertainty on the input, on the independent variable, So we can have both independent and dependent variables having uncertainty and mixed levels of uncertainty, and have it compute the correct weighting for the points to generate the most appropriate plot.